Welcome to Calculus, and before we get started on today's lesson, the question is, what is calculus? Perhaps you might answer limits or derivatives or integrals, and these are all things that you can see if you flip through the textbook or on our syllabus, and we will get to all three of these this semester. But my answer to this question is that fundamentally, calculus is the study of rates of change. The concept of a rate of change, fundamental to this semester, and we will start it right today. Okay, and let's begin with an example, and it's an example that we can think about without too much difficulty. So let's take a car and drive it straight down a road. Okay, so suppose I drive a car. Down a straight road, and I drive it exactly 25 miles per hour for 3 hours. Okay, the question is, how far did I go? Well, you can probably answer this before I even write the question, because you just multiply 75 miles. So we have 25, this is in miles per hour, times 3, which is in hours. We get a total of 75 miles as our total distance we have traveled. Okay, but let's think about if we're starting our journey at, say, 0, and I'm driving straight. Let's think about graphing our position. Okay, so I have 1, 2, 3 hours, and this is going to be miles. I go up to 75, and then like this, 50, 25, and I'm driving this exact same speed my entire journey, which means at 1 hour, I'm at 25 miles. At 2 hours, I'm at 50 miles. At 3 hours, as we calculated, I'm at 75 miles, and I'm starting at 0, as I mentioned. So the graph of my position is a straight line. So let me redraw this one point. Straight line. Okay? So this will be y is p of t. This is my position driving along a straight road. And for example, maybe I will just label when we graph a function, right? This would be the point 2, 50. This would be the point 3, 75. Down here, this axis is in time, t, which is in hours, and this axis is in miles. Okay, now, well, the question, well, look at the board, average rates of change. The question is, what is the rate of change? Well, I've given it to you. Oh, pardon me. Here, this is the rate of change. We know it without even thinking about the graph, but the rate of change here it's 25. But what is the number? Well, 25 miles per hour. But what is this? This is the slope of the line. And, well, let's remind ourselves what slope is. Slope m is, well, one way to think about it is y2 minus y1 over x2 minus x1. I don't have x's here, I have t's. Maybe I will change that. T2 and T1 This would be a formula you remember from previous math class, but another way to write it is you can write it as change in, let's say, p, which is my function, over change in t. And this capital delta here, this is read change in. So change in p over change in t, this gives us the slope. And for example, I have 2 points plotted on the board. This would be 75 minus 50 over 3 minus 2. In fact, we do get 25, okay? So this rate of change, well, it's the same everywhere because I'm driving at this constant rate. I'm driving exactly 25 miles per hour for 3 hours. But the thing that we notice here is that the rate of change in this example is the slope. So the rate of change is the slope. Uh-oh, it looks like I crossed it out. But this is an important concept. Maybe I will put this in star. Rate of change is the slope. And this is an important thing to think about right now because every rate of change can really be interpreted as a slope. So now what I'm going to do is I'm going to change this example slightly. Okay, now, well, I have changed it slightly. I'm still driving down a straight road, okay? But I'm no longer driving at the exact same speed of 25 miles per hour. This is no longer a straight line between, well, my initial place at time A is some location P of A, and then my final stopping place at time B is some location or position P of B. And you see, I don't just go straight between the two. For instance, in this sort of horizontal part, maybe I'm waiting at a stop sign or something like this. Okay, but this is how I am moving down the road. Well, you see, the rate of change is not constant. But what we can do is we can define, so let's define the average rate of change from t equals A to t equals B. This is, well, it's the change in P over change in T, which is P of B minus P of A over B minus A. So all I'm doing here is I'm taking this change in Y, that's another way to write this, and I divide it by the change in T in this case. This is my T axis and this is my Y axis. And what this will give me, well, we see it here. It's average rate of change. And if you think about units, for example, say this is in, this axis is in miles, this axis in hours, the units will be miles per hour, just as we saw in the last example. Okay, so question 1, is this a slope? Well, the answer is yes. I already told you moments ago that we want every rate of change is really a slope. So is this a slope? Answer, yes. In fact, this is the slope of what's called a secant line. And what is a secant line? Well, it's just the line that connects the points A, comma, P of A and B, comma, P of B. You see it in the formula, right? Because Here is the point A comma P of A, B comma P of B. This would be y2 minus y1 divided by, well, T2 minus T1. And the line we can see, if we just connect these two black points with a line, would be something like this. So this green is the secant line. Okay, so the slope of this secant line is the average rate of change on the interval. So here I wrote from t equals A to t equals B. You could also say on the interval A to B, like this. You can also say average rate of change on A to B, on the interval. And this capital A, capital R, capital O, capital C, you will see this in the textbook for average rate of change, okay? So I will put this part in parentheses, like that. Question 2. Well, we have something here that's in miles per hour, right? It's the average rate of change on the interval. The question 2 is this what the speedometer tells you? If you look down, oh, you, or maybe it tells me, but if you're driving down the road in your car, and you look down and you see it says 40 miles per hour, is that this? Is that this? Same units, right? Well, the answer is no. The speedometer is telling you something called instantaneous rate of change, which is coming. Instantaneous rate of change. For example, if you've gotten a speeding ticket before, it's not measuring how far you went over some certain time interval divided by the time. You drove down the road for an hour, you went 60 miles per hour, but you could have gotten in that time a speeding ticket for in a moment going, I don't know, 72 miles per hour, something like this. That is not an average rate of change, that's something different. So question 2, the answer is no, and we will come back to this concept in, well, the very next video. Before I get to some examples with average rate of change of a function on an interval, I want to discuss the difference between velocity and speed. P of t, position, and we are dealing with motion along a line, just like in my first 2 examples. Now, my examples, I was only moving in the forward directions. I was getting in my car and driving straight, okay, down a straight road and only moving forward. I was not backing up, in which case these 2 don't have much of a difference. But if we do have motion along a line, which we will quite often in this course, typically you can think about just moving along the x-axis. For instance, you start somewhere, t equals 0, say you're right here on the line, and then you move forward, you can move back, you can move forward, back, forward, etc. is fine. You're either in a car or you're a particle, something like this. Well, what's the difference between velocity and speed? And today, I'm not talking about instantaneous. I'm not talking about what you see in the speedometer of your car. This comes next time. But I'm talking about average velocity, average speed. Well, if you take the average rate of change of this position, P of t, what is this? This is average velocity on some interval, and I'm not writing the interval here, I'm just talking about the difference between velocity and speed. Now, this includes starting, say right here, and over the course of, I don't know, 2 minutes, backing up 4 feet. So I would go, okay, my change in position, -4 over +2 would be -2. And what did I say? Feet per minute. My point is, velocity can be negative or positive or 0. So velocity can be negative, can be positive, and it can be 0. Okay? It's just the average rate of change, the position function. Where position can move, you can move in the forward direction of the line or in the backward direction of the line. Okay. What is speed? Well, speed must be non-negative. And what is it? It's the average rate of change of the distance traveled over some interval. Again, this is the average speed and distance. So you take the total distance traveled on some interval divided by the length of the interval. And this will be average speed, but total distance traveled is always non-negative, and so speed is always non-negative. And this is the important difference between velocity and speed. Here's our first example. We have f of x is 1 over 2x plus 3. Find the average rate of change of this function from x equals 1 to x equals 3. Well, first of all, let's just graph this. That's one thing nice about the first day, is we can practice graphing a lot of functions that we know and love. So what does this function look like? Well, fundamentally, it looks like 1 over x, except the vertical asymptote, let's see, -3 over 2. So here at -3 over 2, this point is not in the domain of the function. And then at 0, we are at 1/3. Okay, and then it looks like 1 over x. So this comes down, goes through this point, and then it keeps decreasing. Okay, this is more or less the shape, at least for x bigger than -3/2, which that's where my interval is. Okay, so now let's calculate average rate of change. Well, let's see, first I'll put my tick marks. 1, 2, 3. What I want is the change in f over change in x. This is f of 3 minus f of 1 divided by 3 minus 1, average rate of change. And if you want to, you can come to the side, calculate f of 3, which is 1/9, and f of 1 is 1/5. So I get 1/9 minus 1/5 divided by 2. This is, let's see, this would be 5 over 45 minus 9 over 45 over 2. We get -4 over 45 over 2, or -2 over 45. This is the average rate of change. It's negative. Now, does this make sense? If we go back to the picture, yes, it does, because if we think about this point is the point, we have it here. It's the point 1, 1/5. And this is the point 3, 1/9. And we connect these two with a line straight line. This is the secant line, and the slope of this line is the average rate of change on the interval. And we see, for example, this line definitely has negative slope, and so this makes sense. Maybe before I do anything else, we can write an equation of the secant line. I have everything on the board for it. This is kind of maybe a part B, for instance. Well, point slope would be y minus maybe a fifth equals the slope x minus 1. This is one way to write it. This is in point slope form. This is an equation for this green line where the slope of the secant line is the average rate of change over the interval. Here's another example, the cosine. And this is another great function to remember first day. Okay, what does the cosine look like? Well, let's see. We want the average rate of change from pi over 2 to pi, so I will just graph it from 0 to 2 pi. As a recollection of this function, the cosine lies between 1 and minus 1. The cosine goes high, 0, low, 0, high, like this. And this pattern keeps going, but the cosine high, 0, low, 0, high. Okay, this is the cosine. Now, just a comment, if we had sine, it would go 0, high, 0, low, 0, like this. But we are graphing the cosine. And we want the average rate of change here from pi over 2 to pi. Well, immediately, if we think about these the points on this graph, okay, here, and we connect with a straight line, we should get a negative average rate of change because the slope of this line is negative. Okay, but now let's calculate. We want the change in G over the change in Y, right? I'm trying to keep my variables. Now this is Y, and this is, well, G of Y, okay? Trying to keep my letters the same to match the problem. Very nice. Okay, this would be G of pi minus G of pi over 2 divided by pi minus pi over 2. And this is the cosine. Cosine of pi is minus 1. And cosine of pi over 2 is 0. If you don't remember the graph here, it's always good to remember the unit circle here. And, well, what's good to remember for this class? This is kind of a side step. Here's pi over 4, and then we have pi over 6, and pi over 3, and then we have 0 and pi over 2. It's good to know the first quadrant, the cosine and the sine, and then you can use reference angles to get anywhere else on the unit circle. Okay, that was just a comment. But here, pi is out here. Cosine x value minus 1, and pi over 2 is here. We also see it on the graph of the cosine. Okay. Maybe I'll erase my unit circle. Back to this example. So we get the change in G over the change in Y is, this is minus 1 over pi over 2, which is, well, we could invert multiply and we get negative 2 over pi. If I change this just slightly, let's go from 0 to 2 pi. Okay, well, we should know the answer immediately because what is the secant line? We see it in the graph. The secant line, well, you connect 0, 1 and 2 pi 1 and here. Now, what's the slope of this line? It's a horizontal line. The slope is 0. So the answer here, the average rate of change, the answer is 0. And this is it's the change in G over the change in Y here. Or if we calculated, it would be 1 minus 1 over 2 pi minus 0. And the numerator is 0. The fraction is 0. So that's just kind of a comment here I wanted to make. When we notice that the secant line is a horizontal line. Here's one more example of this type. And this is a nice function to think about on day 1 because this is an exponential function, 2 to the x. And we work with exponential functions the entire semester. So before I begin, let's remind ourselves what the graph looks like. Well, this is an exponential with base bigger than 1. Every exponential function goes to the point 0, 1. And then if it's bigger than 1, the base, the graph looks kind of like this, where we have exponential growth. If, as a comment, if the base was between 0 and 1, it would be like this. It would be exponential decay. But here the base is 2, bigger than 1. And I need to go... Oh, maybe I should move down the point 0, 1 because I need to go between 1 and 4, and that is at 2 to the 4 is 16. So I have 1, 2, 3. Uh-oh. Okay, this is going to be interesting. 1, 2, 3, 4. This is going to be fun to graph because my graph is going to go way up into here. So here we're all the way up here at 16. And then at 3 we're at 1, 2, 3, 4, 5, 6, 7, 8. And here was 16. And then we go through 4, go through 0, 1, 2, 1, 2, 2, 4. What we see here, we try to graph this, we really get an idea of exponential growth, at least a little bit, because it increases so much. Okay. Okay. So here is my graph. Y is 2 to the x. So let's find an equation of the secant line. Okay, well, the slope of the secant line is the change in y over the change in x, or I could have written change in f over change in x. It will be 2 to the 4 minus 2 to the 1 over 4 minus 1. Okay, so this is 16 minus 2 over 3, 14/3. This is the slope of my line. Maybe I'll write this one in both point slope and slope intercept just to practice. So I can do y minus, actually I'll label some points. This is the point 1, 2 to the 1. And, oh goodness, well, maybe I won't label that one. I'll just have this one. So it's y minus 2 is slope x minus 1. And then this would be, well, I'll do both and then I'll label it. This is 14/3 x minus 14/3 plus 2. 2 is 6/3. So we have 14/3 x minus 8/3. So let me label these two different types. This one, slope, point slope is here, and this one, slope intercept, is here. And if we wanted to graph this secant line, I'd like to end with this example. This is one of the textbook exercises, and it's a little bit more involved than the ones we have done so far. So let's discuss why. We have a balloon that is inflating, and we assume it stays as a sphere as it inflates. We want to find the average rate of change of the volume with respect to surface area as the surface area changes between 4 pi and 9 pi. So what do we want here? We want the change in volume over the change in surface area, but the formulas that we know give volume and surface area as functions of the radius. So we know that volume is 4/3 pi r cubed. The surface area is 4 pi r squared. But what we want, as I mentioned, change in volume over change in surface area. Now there's a few ways we can do this, and this is something, this idea, something we'll come back to more this semester. But for now, way number one, maybe I will just discuss. We can write volume as a function of surface area. And how can we do that? We, for example, solve for r here. So we know that r is, we can just divide, we get s over 4 pi. This would be r squared. We know that the radius is always non-negative, so it's going to be the positive square root. And then, well, we see a 4 pi r squared here. And then we have a r over 3. So this would be s. And then say s over 3 square root s over 4 pi, which we can then, maybe I'll take one more step here. This would be s to the 3/2 over, this will be 6 square root of pi. Okay, so this is one way. Now you have volume written as a function of s, and we just evaluate v of 9 pi minus v of 4 pi divided by 9 pi minus 4 pi. This would be fine. But if you didn't want to go through this, you see, all we really need is, we don't need the whole volume as a function of s. We just need the volume at 9 pi and the volume at 4 pi. So I'll mention this other way, which we get the exact same answer. I will just mention this now. So when 4 pi is here, and when 9 pi is here, so this is, I'm just solving for the radius only for these two special cases. These two surface areas, what is the radius? So here we see that r is 1, and here we see r is, well, it's going to be 3 over 2. And now we can get the volume in each of these cases. Now the volume here is just 4/3 pi, and the volume here is 4/3 pi times 27 over 8, which is, we have 9/2 pi. Okay? So now we see for this s value, here is v. For this s value, here is v, like this. Or you could just evaluate this function at the two s values and you get the exact same v. I was just showing two different ways to go about it. Okay, and then now that I have this, I will erase this part to finish the problem. The change in v over the change in s will be, okay, 9/2 pi minus 4/3 pi divided by 9 pi minus 4 pi. We get, well, this is 5 pi. We get 9. Oh, well, you see I can divide everything by pi, right? I have a pi in every single term, and pi over pi is 1. So I have 9/10 minus 4/15. This is going to be 27 minus 8/30. We get 19/30. And this is in, well, my numerator is in inches cubed, and then my denominator is in inches squared. So the units would be like this, inches cubed over inches squared. This is our final answer here.